So in order for us to fully understand how the how this PV works, or the mechanism of the working mechanism, we need to first understand what are semiconductors. So materials are normally divided into three kinds. We have the metals or the conductors, and we have the semiconductor as well as the insulator. And so the difference between this one is based on its electron energy levels. So if you can see from this side, we have the red part as the valence band, and the purple one is the conduction band. So for metals, the valence and the conduction bands are actually overlapping. So it means that the presence of electrons on the other side can actually just interchange. So they can be excited. So they can allow excitation of electrons to flow through the empty band with a little bit, just a little bit of a push. So it means that with this flow of electrons, then it's highly conductive. So the electrical conductivity is very high for the metals, for the conductors. While on the other hand, the insulators have a very large band gap, and so there is a really greater energetic difference between the valence band and the conduction band. So in this case, the flow electrons are inhibited. So that's why insulators are very poor conductors. They don't allow the flow of electrons. But if you look at the semiconductors, we have a good amount or a good value of band gap in between. So this is so basically the semiconductors are the properties are in between metals or the conductors and the insulators. But in natural state, the semiconductors are quite poor conductors, primarily because they require a current requires the flow of electrons, and semiconductors have the valence bands filled already. So these are already filled with electrons, so they don't really allow the flow of electrons. So in order for the conductivity to increase, it can be increased by the increase of temperature, or we can change the materials into by doping the materials, the semiconductors. So doping of the semiconductor changes the conductivity of that semiconductor, and this doping results into two kinds of materials: the N-type, which is there is an excess of free electrons, and we have the P-type. We have the positive holes of the semiconductor. So once we understand that semiconductors are in between, the properties are in between metals and insulators, we now try to understand how it works with the use of in response to solar radiation. So when we have a semiconductor, for example, in this part here, if we have one semiconductor and there's a solar light and there are photons here. So once the photons reach the semiconductor, it bounces off the electrons and forming these two. They have a hole here and we have the electron here. But naturally, they are very attracted to each other. The electron and the holes are attracted to each other. So they tend to recombine automatically. All right. So if we use only one semiconductor, they recombine easily. So this one doesn't really allow the flow of electrons anymore because they just recombine together. So in order for us to have these electrons to flow somewhere else, then we need to provide some sort of a gap between. So this is what we call now the two kinds of semiconductors being sandwiched together. So we have an N-type semiconductor, and we have also a P-type semiconductor. So these are a negative part where there's an excess electrons, and we have the positive part here. We call this part as the p-in junction. So most of the solar cells are like this. So for example, when solar light comes in, as I mentioned earlier before, it bounces off the electrons. But instead of recombining directly, the electrons now are now guided towards a system here, or a line here. Instead of recombining directly together, the electrons first travel towards here. So that's why the travel of these electrons and then recombine together with the holes here. So this red part is the electrons, and this is the hole, and then it recombines together with the hole. So instead of combine together, it goes first through a flow. And this flow of electrons is what is the generation of electricity. So you can see from here, electricity is generated. So this N-type p-n junction provides that situation of electron flow or electricity generation. But of course, if you look at the system, not all of the light energy or the solar light energy are actually absorbed by this p-n junction or the semiconductors here. A lot of this light energy are actually emitted as a waste heat. So they are only a small part of the light has been absorbed and made into usable energy or electricity. So let's see for what happens in the conversion of this light. So as we can see, the energy transformation of solar PV, if we have a lot of light energy coming from the photon itself, this is the area here, this amount of light or the light amount of energy. Once it reaches the solar PV, only a small part is actually converted into electrical energy or electricity. Most of the parts coming from the bulk of this one is actually released as heat energy. So in this case, this is what we call as waste heat. So it's just heating up at the bottom side of the solar panel or even towards the surroundings. So for the electrical energy conversion, it's only around 16 to 25% in most cases. So on average, we have 20% of conversion. So from light, if you have 100% here, only 20% is actually converted into electricity. So this is a 20% efficiency. So to calculate this solar power coming from the sun, we can calculate solar power as efficiency times the insolation times the area of that solar panel. So the area of the solar panel, of course, refers to this area here. So if we have a lot of solar panels all over, so in pins, if we increase the area, so we are also probably increasing the solar power. So it is directly related. And insolation is, as I mentioned before, is the amount of power per unit area, so watts per square meter. So this is coming from the sun. So it depends on the condition of the day or the location of your solar PV, where you're located. If it's a shaded area, then the insolation will be lower. But if it is totally exposed, like directly perpendicular to the sun, then we will be receiving a maximum amount of solar energy. Of course, the efficiency will be depend also on the kind of device that you have, the solar PV. So depending on what sort of PV that you have, you can have about 20% of conversion efficiency. So this is how it looks like in most cases for the use of solar PV in homes, in houses. So we have the solar panels here. So the panels are put into modules here. And so once we have the light producing the direct current electricity, so the direct current goes towards the inverter here, all right? And then this inverter is actually converting, so we need an inverter to convert the direct current into usable alternating current, because we use alternating current in our homes. So this alternating current can be provided as a grid, if it's grid connected, a grid tie, you can give back this one excess energy that you have to the grid so for the grid to buy, or you can just reuse this one towards your use inside the house, depending on how much you can use inside the house and how much is the capacity of your solar PV panel. So we have to understand this one on how to identify or how to calculate how much power can you generate from your solar PV, and also how to calculate some of, or how much need of solar PV size do we need depending on the requirement in your household, for example. So we need to understand how to calculate these things. The next slide gives an overview, a short video of the overview of how solar PV works.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses two different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the two types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades.
So let us now take a look about the various components of a photovoltaic array system. So normally in a solar PV, we are referring to that one as modules or panels. But if you look at the basic unit of that panel, we can see a cell, one solar cell. But this one solar cell is actually quite low in terms of its energy production. So one PV cell can only produce about or power about 1 or 2 watts of power for each one of the cell. So that's why the cells are combined together to form into a module. And this module now has a number of cells together, and we call this one a solar panel, as we can see from many of the structures that we have. And this solar panel could be in the number of 36 cells or 60 cells or 72 cells, depending on the capacity of your whole module. So these are sealed together for easy handling. So it means that you put together as one module to handle together. So for each panel, normally the capacity is around 250 to 400 watts per panel of power production. All right. And so we have the PV cell here, and then we have the PV module, and then these module or panels are now linked together to form into a solar array. So this array is what we call as groups of panels or modules making up the whole of the array. So this is now what we see on houses, on the rooftops of houses, so that it can produce the amount of power that is needed for the specific use. So for example, if one solar array has a capacity of 5 kilowatts, so to make up this energy or power production, then this array could be based on 20 panels of 250 watts for each panel. So we can have 5 kilowatts. Or you can have a system that has 16 of 300 watts panels. So both of these could be possible to design a solar array. So you can see that the arrays has to be even. So you have to make sure that during the installation, they have even installation of the solar panel systems.